the microphone over to the two discussion leaders, Reinhard and Mark. But before I do, I'd like to thank again all the speakers from this afternoon for great talk.
Why don't you grab that, Reinhard? So we thought we would limit this to 2 questions based on the experience from the last discussion of not even getting through one. So our 2 questions are written up there, and we have one observationally focused, one theory focused. All right, so, well, you can all read. I won't read them to you because everyone's tired.
One thing that confuses me, and I'd like to hear from the experts. So, in terms of what I think scale with Redshift, the first question. I was starting to adopt this picture where star formation, all star formation happens in giant molecular clouds. And in a given giant molecular cloud, things are locally regulated. There's some turbulence that's drifting, supersonic turbulence, and a certain fraction of a giant molecular cloud turns into stars with an efficiency that's roughly always the same, just local physics. Now, if you then want to change things with Redshift or with mass or anything, you have to basically change the rate at which you turn gas into molecular gas. And that's how I was sort of thinking about the picture. But now I got very confused when Linda showed this morning that along the specific star formation rate, along the specific, what is it called, the star formation sequence, perpendicular to it, things scale that the distance from the median scales with the molecular mass to the 0.5 or something. So that suggests there is another parameter. And Reinhard was saying, well, it has to do with the surface density of gas, but what is the surface density of the
volume density?
So the picture that everything is regulated by just the rate at which I turn gas into molecular gas, and then it is a fixed rate. Is that should I leave that over?
If you go back to some of the basic picture, you have collapse on a free fall time scale in a turbulent medium. Mark's work. Then you would think there should be dependence on local volume density. And if such a parameter varies, and that could vary, it does vary in the Milky Way, that's been shown, then you
what varies? I mean, I'm talking about the density structure of individual GMCs are different. A GMC in the outskirts of a galaxy has a different density structure than the inner part of the galaxy?
Well, in this case, where you would say a more gas-rich system, that's the other parameter which varies as you go up and down. The local volume density, the galaxy does not get bigger. If anything, it gets smaller as you go up. The volume densities could go up, the free fall times could go down, and so that looks like a lower depletion, a smaller depletion time scale.
Yeah, I'd add that the statement that there's sort of a constant efficiency should be understood as per dynamical time, and the dynamical time is not required to be the same in all molecular clouds. In local star-forming galaxies, the first order all molecular clouds look sort of the same in a normal star-forming disk. But even in the local universe, if I go look at ARC-220, for example, some major merger, right there, we know the mean density of molecular gas in ARC-220 is way higher than it is in a Milky Way molecular
But is
cloud.
that because I pack more GMCs in a certain volume and each individual GMC looks still like a GMC?
No. No.
That's a crucial thing.
Okay. Yes. I mean, in the way we know this, I mean, one piece of evidence, and I can't remember who showed this plot, maybe in Linda or maybe in you, the HCN to CO ratio. Right, so HCN is a dense gas, is a tracer that doesn't start getting excited until the density is sort of 10 to the 4, 10 to the 5. CO can be excited at closer to 10 to the 2. So if the density structure inside the GMCs were exactly the same, that should be invariant, and it observationally isn't.
Let's face it, at this point for the distant universe, that's a conjecture. However, in the local universe, in the Milky Way, Charlie Lauder and others find that, okay? So the depletion time scale does vary, so to speak, in local clumps. Too bad that David disappeared. David is still here. Maybe you want to say something about, you know, the Herschel picture, how remarkably, to some extent, stable, so to speak, the properties of the dust is. You want to?
Here, hi.
Yeah, but
All right, turn this off. I've rebooted.
so I guess everyone agrees. No, it's true that we were surprised by the universality of the ACDs of galaxies in the infrared, even though there is a small variation. And the ACDs are very sensitive to the geometry of the star formation, of the destruction of the dust grains, and up to redshift 3, we don't see major evolution. And in fact, one thing I didn't show is that even when we look at the ACD shape as a tracer of star formation rate density, we have used an index called IR8 index, and when we compare that to the projected star formation rate densities with ALMA, it's also correlated very well. So that goes together in the direction of saying that indeed there is no major change. There is a slight, a small evolution. For example, main sequence galaxies have, let's say at high redshift, have a T-dust which is larger than at low redshift, but it's marginal, and they are a bit more compact, but it's a very tight evolution, no major difference, I would say, from Herschel.
One question I would have is on the group at Suckley and our group tend to agree from different perspectives quite well, where I think our view is moving apart a little bit, and Linda mentioned that, is the bimodality. So the fact that, you know, you look at the extreme local star formers, up to 20, there indeed the gas is rather warmish, and it's really dense. So the dense gas fraction is very high. And so that's a different kind of a object, so to speak, from your, you know, disk galaxy at redshift 0. So I think, could you maybe say a few words how your views develop on whether there is really truly only two modes, or whether you can sort of basically have a mixture of different components of density, you know, a distribution function, where then the most extreme one is only reached in the most extreme environments.
It's true that it's true that there is no clear evidence for a true bimodality in the sense of two clouds clearly separate, and part of the tension of the gap that you were seeing in the Schmidt-Kennicut relation, for example, before, was coming from the alpha CO, and then it all depends on do you jump from one alpha CO to the other. For the moment, the comparison of the dust masses from the infrared and the alpha CO, as you said, are very consistent, but there is clearly some galaxies filling in between. Now, whether you need two really physical different mechanisms, or just some other, let's say, dynamical instabilities triggering stronger star formation, it's not obvious. One thing that is puzzling to me is that simulations of gas-rich galaxies with 50% gas, when, for example, the work of Florent Renaud, I don't know if he's here, was showing that, for example, when you have local galaxies with 10% of gas, it's the compressive turbulence that is the main driver of the starburst when you have a merger. But then when you go at redshift 2, where you have 50% of gas, there has been some simulation showing that there, the gas is so turbulent that the merger doesn't impact anymore. So we don't know how to make a starburst from a merger. So this two mode is not of use to me anymore when you have a high gas fraction, because you don't even know how to make a starburst with a merger.
Maybe I can, before we go to Avishai. Alison, I'd like to go to your observations. Since you do see a significant change in the interstellar medium, this is the ionized interstellar medium, could you remind us perhaps of how large these changes in the ionization parameter and the density are compared to your local redshift 0 disk galaxy?
So you wanted to know about the ionization parameter and what? What else?
And also the local volume density of ionized gas from the sulfur 2
Sure,
or oxygen 2?
So we measure electron densities with O2 primarily instead of sulfur 2, but we see about 200 to 300 per cubic centimeter, which is elevated with respect to what is typically assumed in the local universe, but it's not unheard of in the local universe.
How large is the typical number?
You'll see anything ranging from about 10 to about 100. It's usually 10, but in the most extreme, dense star-forming regions locally, you can see up to 1,000, but that's extremely unusual.
It should be understood, I mean, just with respect to that, there's a huge amount of selection bias in there. I mean, there certainly are H2 regions that have densities of 10 to the 4 or 10 to the 5. You just don't see them in the optical because they're hypercompact and they're buried under 500 magnitudes of extinction, and you only see them in the radio. All right, and there are probably H2 regions that have densities of 1. You, again, don't pick them up because their surface brightnesses are too low.
I would like to make the same question very specific and to ask Reinhard and David, etc. In the language of star formation rate being some factor, epsilon, times gas density over local freefall time of the star forming region, is there observational evidence for epsilon being bimodal or different at different times or different galaxies or different sequences? Or can we have it the same epsilon all the way through? Considering the local freefall time.
Yeah, we can't. We really don't have local observations, do we? That's the problem. We have galaxy averages at this point in the molecules, so I'm afraid I can't answer that. Of course, in the galaxy averages, we know if you have Q equals 1, whatever your average or your variations in the freefall timescales are, it sort of get latched to a dynamical timescale at some level. So even if you could tell, if you really strictly have Q equals 1, then you wouldn't be able to tell. But I'm afraid these traces we have are not yet spatially resolved.
And even in the BZK galaxy that redshift 2, where we're seeing the bimodality, that was in gas mass. But if in gas mass, but if you use the freefall, if you divide by the dynamical time, you don't have any more. We didn't have any more the bimodality. So our interpretation was just a question of how efficiently you make the dense HCN gas in some galaxies. And simulations again of Florent Renaud and Frédéric Bourneau were telling me that the PDF of the normal isolated galaxy without a merger were not enough populating the dense gas to make the starbursts. That's why we were thinking it was mostly mergers. And but again, at high redshift, that may be the thing which is different. Is that makes the galaxies different at high redshift. That they are much better self-regulated. Apparently at high redshift, that means that even if you put a merger, it doesn't make a big impact.
So maybe we could summarize sort of that section of the discussion. My summary would be, I'm more impressed currently by the evidence, how similar the typical main sequence star forming properties probably are to the local universe than not similar. Yes, it's higher density, of course, scaled up versions, densities are probably somewhat higher, ionization parameters are higher, things are closer together. Still, it's not a huge factor for the main sequence population. So if you accept that, I should say, if we were now in a meeting of millimeter, submillimeter astronomers, that would be violently objected to. Because the millimeter community, indeed, very much still sees the Madar-Lilly plot and recalls that if you look at the submillimeter view of the HDF, you may recall that, there's 3 objects in there, and they have this, totally a significant contribution to the far-infrared luminosity density, and therefore, per object, you have this, enormous amount of star formation rate. And for them, the UNOC phenomenon is an extreme phenomenon, which then at high redshift is still more extreme. I just want to point that out, that it's really a cultural difference between the UV optical simulator community on the one hand, and then those people who have come typically from outliers and really have studied the most extreme objects. Mark, you want to?
Oh, well, I was going to let someone else talk. So.
Okay.
Or Dave, I think David wanted to comment on that. Then I could bring up the theory question.
I had an impression looking at what the theorists continually present, and that's the stellar mass to halo mass relationship, and to show that that has been rather stable over time. I would think that that is a global estimate of how much change there really has been in some efficiency factor. So am I misinterpreting the value of that diagram and answering this question in some direct way? That yes, there are all these different effects that changing one way or another, but perhaps by coincidence they all conspire to each other to then end up giving an average efficiency at a given halo mass that's similar at high to low redshift, despite changes in metallicity and accretion rate and the typical size galaxies and all these other things that we've been talking about during this conference. So I'd love to hear people's reaction to that sort of simple view.
Course, on the other hand, if you look at the feedback, the wind phenomenon is a relatively rare phenomenon in the local universe. You have to go to the outliers to see that well. Okay, while at high redshift, everything has an outflow, so that does look different. Yeah?
Well, yeah, many things are different. I'm saying that it's all conspired to an average, not something that's very stable.
Okay, maybe we can go to the theory question for the last 7 minutes. So, what prompted me to put this up is in the last day or two, I have seen, let's see, so we saw the fire talks where feedback rules the world and your small-scale star formation recipe is utterly irrelevant. All right, we saw sort of something intermediate where, yes, the scaling of the star formation rate with the small-scale star formation recipe was sublinear, but it wasn't zero. All right, we saw a talk where you got totally different answers based on this subgrid recipe for how turbulence works, and it was really important to have the local star formation law. All right, and I'm sure there are other answers out there. So the question is, are we making any progress, or are we basically just doing, and I'll quote Martin White on this, SAMs with resolution problems?
I'd just like to amplify your question a little bit by saying that I'm trying to figure out how this feedback or theory stuff relates to a bathtub picture, in which basically you make all the stars that you are given gas in order to make. And where is the feedback? Where is the control? You just make stars.
Well, okay, so I'll take a swipe at the bathtub question, which is, so I think that if what you're interested in is demographics, bathtubs are, if what you're interested in is the demographics of stars, probably bathtubs plus outflows are all you need. If you're interested in knowing how much gas lives in galaxies, then you care a tremendous amount about the feedback. And the other place you may care a tremendous amount is if you go to dwarf galaxies, which may not be bathtubs because they've got such long depletion times. Right? It's reasonable to assume that the Milky Way is in bathtub in equilibrium because its depletion time is way less than a Hubble time. The SMC's depletion time is not way less than a Hubble time. It's way more than a Hubble time. So treating it as a bathtub is maybe not a good approximation.
Thank you.
I guess this bathtub model might work only in a very long time averages, even for other galaxies. If galaxies are bursty and you average over many different bursts, then there is some regulation with the overall gas inflow, how much it gets in, how much it was ejected out. If you look at a small time scale of like hundreds of millions of years and galaxies are bursty, then there is no bathtub model. And only at late times or in massive galaxies that are much less bursty, you can get something to standard bathtub.
I just want to make an interesting comment based on a paper by Nelson et al. From the illustrious simulations. So they play around with different feedback, weak feedback and strong feedback. And this is for Sandra's question. It did not make a big difference to the overall star formation rate, because when you had strong feedback, you also had strong recycling, and the stuff came back. Eventually, if you looked at the input of gas, net inflow, just around the galaxy, it was almost the same when you had strong feedback or weak feedback. So in the bathtub model, you can have both ways, and some global features will not change. But my answer to the question is yes.
So one comment connecting maybe the two questions. I had the feeling that what Reinhard was saying is that high redshift galaxies are surprisingly regular in their properties. And on the other hand, the recent simulations all agree that the evolution of those galaxies is very violent. Sometimes you have a complete removal of the gas in some giant outflows. You have a lot of also gas holes inside the galaxies where the latest starburst took place. And I'm wondering whether there is not a discrepancy here. So my question is, can we, in observations, have an idea of the violence of the gas flows in the disk, around the disk? And I think it's a key point for us simulators to understand our feedback models, is to look at the fate of the gas in the disk, but also in the CGM, and that's probably will give us much more constraint than the actual star formation rate or the stellar content.
Yeah, so I have a comment on Avisha's comment that feedback matters not as much as one might thought. But if you assume feedback is 0, and we know that long ago, you're going to overproduce star formation by factor 3 to 4. So it does matter. So as I suggest in my talk, it's the global feedback. In other words, you have energy and momentum ejection over time. Therefore, you're raising the entropy of the gas. So it's the bathtub. It's building the bathtub, splashing water out, constant. So in the end, the amount of water coming in will be reduced by a factor 2 to 3 eventually. And I think I agree with Norman's comment that if you look more around galaxies in the CGM, look at the line features, emission or absorption, they'll give you a much more strong constraint on the feedback from the other side.
I'd add another place to get strong constraints is from the resolved star formation histories of local dwarfs in particular, where you can actually get pretty good from CMD constraints on what their star formation histories look like. I mean, we saw that earlier today. Earlier in the meeting.
On your question, I think you will see in the next years another development, which is obviously high-resolution, spatially resolved studies of the various components which we've been discussing at high redshift, in particular in the gas. Unfortunately, these observations, any number, so that they would convince you as theorists, will be very costly, so it will take some time, but it will happen. I mean, the first 0.1 arcsecond CO or whatever map of a high redshift galaxy is soon to come. I mean, we'll see it, and likewise, the first maps of the winds and so forth, I see that coming. Of course, with it will come complexity. Let's just face it. I mean, the maps will, the CO map will not look like the H alpha map. And then we will all be thrown into desperation on the extinction business and so forth. So it's not going to clear up everything, but the fine detail will come.
Yeah, I'd point out the Milky Way star formation community also can't agree on the importance of feedback and what feedback should be put in, right? And we've had better than, 10th of an arc second resolution of the Milky Way for a while.
Just to comment on what Renyu was saying, you're right that if we turn off feedback altogether, we have a problem in terms of we make too many stars, but that's because you're looking at a statistic that says something like, what is my stellar galaxy mass function? But if you would look just at what do I produce for the specific star formation rate function, the star formation rate is a function of stellar mass. And we have done these experiments, and you find the same answer. It doesn't matter. I can turn off feedback, I can turn it on, I can make it momentum-driven, energy-driven. My star formation rate sequence looks exactly the same. Okay, and that's hinting at certain things have just no information content regarding the feedback. That you get the scaling with redshift comes out no matter what you do. But
supply, so gas coming in, you're going to form some fraction of it.
Right. So if you now link it to halo mass, you say, okay, but now I produce too many stars in a given halo. Then correct. So if you want to constrained feedback, that's where you have to look, in that area. Or about, what does feedback do to the properties of the gas around you. But there's certain information that has no information about. Yeah, we would be in a big problem.
All right, I think this is the last comment, Avishai. And
I just want to add something we learned in John Forbes' talk, for example, that feedback has different phases. One of them is throwing out gas and outflows. The other one is affecting star formation. And that's not the same thing necessarily. There's a long-term effect. If you lose gas, you affect star formation in the future. But at a given time, you can affect star formation without throwing the gas at all. This is an issue which we have to take into account and complicates matters.
All right, and I think we are at 6 o'clock, so good evening, everyone.
Thank you.
Thought we would limit this to 2 questions based on the experience from the last discussion of not even getting through one. So our 2 questions are written up there, and we have one observationally focused, one theory focused. All right, so, well, you can all read. I won't read them to you because everyone's tired.
One thing that confuses me, and I'd like to hear from the experts. So, in terms of what I think scale with redshift, the first question. I was starting to adopt this picture where all star formation happens in giant molecular clouds. And in a given giant molecular cloud, things are locally regulated. There's some turbulence that's drifting, supersonic turbulence, and a certain fraction of a giant molecular cloud turns into stars with an efficiency that's roughly always the same, just local physics. Now, if you then want to change things with redshift or with mass or anything, you have to basically change the rate at which you turn gas into molecular gas. And that's how I was sort of thinking about the picture. But now I got very confused when Linda showed this morning that along the specific star formation rate, along the specific, what is it called, the star formation sequence, perpendicular to it, things scale that the distance from the median scales with the molecular mass to the 0.5 or something. So that suggests there is another parameter. And Reinhard was saying, well, it has to do with the surface density of gas, but what is the surface density of the
volume density? If anything, it gets smaller as you go up. The volume densities could go up, the free-fall times could go down, and so that looks like a lower depletion, a smaller depletion time scale.
Yeah, I'd add that the statement that there's sort of a constant efficiency should be understood as per dynamical time. And the dynamical time is not required to be the same in all molecular clouds. In local star-forming galaxies, the first order all molecular clouds look sort of the same in a normal star-forming disk. But even in the local universe, if I go look at ARC-220, for example, some major merger, right there, we know the mean density of molecular gas in ARC-220 is way higher than it is in a Milky Way molecular cloud.
But is that because I pack more GMCs in a certain volume and each individual GMC...
The microphone over to the 2 discussion leaders, Reinhard and Mark. But before I do, I'd like to thank again all the speakers from this afternoon for great talk.
Why don't you grab that, Reinhard? So
the picture that everything is regulated by just the rate at which I turn gas into molecular gas, and then it is a fixed rate. Is that? Should I leave that over?
If you go back to some of the basic picture, you have collapse on the free fall time scale in a turbulent medium. Mark's work. Then you would think there should be dependence on local volume density. And if such a parameter varies, and that could vary, it does vary in the Milky Way, that's been shown, then you
What
put
varies? Are we not talking about the density structure of individual GMCs are different? A GMC in the outskirts of a galaxy has a different density structure than the inner part of the galaxy?
Well, in this case, where you would say a more gas-rich system, that's the other parameter which varies as you go up and down. The local volume density, the galaxy does not get bigger.